Hello everyone, my name is Yoon Byung and I will talk about robust self-supervised learning and our of distribution detection. Let's begin. Today I will tell you about these contents. I would like to show you experiment results. However, I failed to get results, so I will talk about my failed experiments. First, I will explain about method that I referenced for understanding my experiments. It will be a short review of my midterm presentation. In our OCL paper, authors aim to obtain comparable robust accuracy over state-of-the-art supervised adversarial learning methods with efficiency. While some recent works propose semi-supervised adversarial learning methods that utilize unlabeled data, they still require class labels. The most popular approach to achieve adversarial robustness is adversarial learning, which trains the model with samples cultivated to maximize the loss on the target model. They propose another adversarial attack for unlabeled data, which makes the model confuse the instance-level identities of the cultivated data samples. ROCL, a self-supervised contrastive learning framework, is presented to adversarially train a robust neural network without labeled data, which aims to maximize the similarity between a random augmentation of a data sample and its instance-wise adversarial perturbation. Random augmentation is identical with SimCRRs. In this algorithm, Bx, epsilon is the L-infinite norm ball around X with radius epsilon, and pi is the projection function for norm ball. The alpha is the step size of the attacks, and sign function returns the sign of the vector. In instance-wise attacks iteration, adversarial example that maximize the contrastive loss is generated. Furthermore, LCE is the cross-entropy loss for supervised training, and I is the number of attacks iterations. This formulation generalizes across different types of gradient attacks. For example, projected gradient descent starts from a random point within the f plus minus epsilon and perform I gradient steps to obtain an attack xi plus 1. Specifically, perturbations are generated on augmentations of the samples to maximize their contrastive loss such that the instance level classifiers becomes confused about the identities of the perturbed samples. Then the similarity between clean samples and their adversarial counterparts using contrastive learning is maximized. The simplest and most straightforward way to defend against such adversarial attacks is to minimize the loss of adversarial examples, which is often called adversarial training. Take L2 norm ball as an example. Suppose the norm ball of radius epsilon is centered on the original image, and the transformed image for the pretext task, as you did in SimCRR, can be created. The adversarial attack image is present on the norm ball by the projection function. On the left, first equation, term with superscript in T is adversarial examples, and T prime is transformed inputs. The neural network for adversarial attack learns to view negative images, transformed images, and adversarial images as one positive set. Through this process, it attempts to include more negative images in the positive set, not the original image. As you can see in left second equation, with the constant lambda rate of learning for robust contrastive learning and learning for adversarial attack is scaled. Detecting out-of-distribution inputs is critical for safely deploying deep learning models in the real world. Existing approaches for detecting out-of-distribution examples work well when evaluated on benign in-distribution and out-of-distribution samples. However, in this paper, they show that existing detection mechanisms can be extremely brittle when evaluating on in-distribution and out-of-distribution inputs with minimal adversarial perturbations which don't change their semantics. This paper proposed an effective algorithm, ALOE, that substantially improves the robustness of out-of-distribution detectors, where F-theta X is the softmax output of the neural network. In addition, this method leverages an auxiliary unlabeled dataset, DOE, while existing method directly uses the original images X in DOE as outliers. ALOE creates adversarial outliers by outsearching within the epsilon ball that maximize the KR divergence between model output and a uniform distribution. The overall training objective of FALOE can be formulated as a min-max game given by the equation on the slide. To solve the inner max of these objectives, they used the projected gradient descent method. With the idea of two papers, I tried to propose an out-of-distribution detection methodology for a neural network pre-trained with self-supervised learning. Although many papers after Odin paper have already proposed a methodology to prevent high confidence prediction in OD dataset by looking at prediction confidence score. To the best of my knowledge, there was less or no paper analyzing OD detection for pre-trained self-supervised neural networks. The network in ROCR paper has a projector network and ResNet as shown in the above slide. Through adversarial self-supervised learning, it is ensured that outputs of positive sets are mapped similarly and outputs of negative samples is far from them. As you can see in the picture above, the positive set is an adversarial image and positive image and transformed image. If the image data is in distribution inputs, the output among positive sets will be closed mapped and negative samples will be mapped away, as mentioned above. The outputs colored blue in the figure will have similar value and the outputs colored red will have different values from the other blue ones. But if out of distribution inputs come, the result may be different. In the case of positive sets, including the adversarial attack image, they will have a completely different output from each other. So it is normal that the output colored red on the figure have different value. However, through inlier attack, the data of the of distribution may have similar outputs as in distribution data. My plan is to apply an inlier attack to the data of distribution and pass the data to ROCL neural network and check if the network was robust to the attack. And for the experiment on robust out of distribution detection, I wanted to make sure that network in the ROCL paper maps the in-distribution data given Gaussian noise to robust output. And in the same, checked with out of distribution data with Gaussian noise. The goal was to experiment for out of distribution detection using robustness of a neural network, but sadly I have not yet achieved good results. Like paper of ROCL, I use CIFAR 10 dataset and ResNet 18, and the paper used two RTX 2080 GPU, so I use GPUs of similar performance, but torch distributed module, which are OCL authors utilized for multi-GPU processing, is not worked well in my environment. Single GPU VRAM is short age for these experiments, I think. If you have any idea about it, please let me know and I will fix my experiments. Thank you for listening my presentation. If you have any question, just let me know. Thank you.